Oh, good afternoon, everybody, and welcome to this session on optimization, control, and machine learning. First session in that topic. We have 3 speakers, and I'm going to keep approximately to time in case people want to, in the 4th session, go somewhere else. But it does mean there won't be quite so much pressure, and we should have time for some questions as well. So I won't take up any more time. The first speaker is Dr. Luis Fernando Garcia Rodriguez. So, Luis, if you'd like to take the floor, you can take it away, basically.
Okay, thank you very much, Professor. Good morning, everyone. Let me share you here my screen. I think you're all seeing it, right?
Yes, I can see it.
Okay, fantastic. So let's start the presentation over here. So yes, my name is Luis Fernando Garcia Rodriguez. I'm finishing my PhD at the University of Sao Paulo. I have worked along with Professor Emilio Silva during these years by making topology optimization of incompressible and compressible turbulent flows. And the current presentation, I will show you some results about incompressible turbulent flow by considering the continuous adjoint method. I'm part of the Research Center for Gas Innovation from Shell Oil Company in Brazil, and I would like to thank also to my sponsor CAPES Foundation for being part of this presentation. So this is the contents of the presentation. At first, I will start with a little bit review about what's topology optimization of fluids. What we do here is optimize the fluid flow performance through a domain. So for example, we've got some inlet and outlet boundaries, and we discretize it by means of FEM or FBM methods. And then we solve the topology optimization formulation until we get an optimized topology where we changed some of the cells by solid regions and the other cells are fluid regions, which then are post-processed and can be built as prototypes to be tested. So the way as we do it in topology optimization is by means of penalization terms at the states equations. So for example, we've got the momentum equation and we use this penalization term at the end, which help us to change the cells that were discretized by changing their permeability. So when we've got high values of the penalization term, we can change the cells by solid regions, and backwards when we've got low values of the penalization term, we can allow the fluid flow go through and create new paths that are non-intuitive and maybe new designs of topologies. So topology optimization, it started in the 2003, and plenty of works have been performed at laminar flow, and turbulence regime is now being tested. This is actually the field of my research during my PhD. And especially in the discrete adjoint approach, there have been some works made at turbulent flow, but the continuous adjoint approach, there are like some spaces that have to be like searched. So at first, well, we want to develop topology optimization for incompressible turbulent flow by considering the continuous adjoint approach and the finite volume method, improve the solid fluid boundary definition, and determine the influence of the adjoint distance calculation to actually calculate the turbulence model or the adjoint turbulence model, and apply this to improve fluid flow devices at 2D and 3D domains. So everything starts by getting the primal states equations. We consider the Rans equations, and we consider the Boussinesq assumption to treat turbulence. And due to the literature review on topology optimization of turbulence modeling, we have started by considering the Sparatal-Maras turbulence model. We have given some good results at the discrete adjoint approach. So in the topology optimization formulation, we use this gamma variable to control the permeability of the domain cells, and we consider this material distribution equation with different optimization parameters that have to be calibrated in order to obtain almost like a 0-1 behavior that tells us clearly, okay, this cell should be fluid and this cell should be solid, and try to avoid this linear behavior that lead us to gray regions. We also, as I told you before, modify the states equation. So like the Navier-Stokes equations are modified with the penalization term. the spiral Maras turbulence model is modified as well. And at this research, we have innovated because we have also penalized the near wall distance calculation to calculate the adjoint turbulence modeling. And we have also included the volume fraction constraint, which help us to indicate the amount or the percentage of the domain that needs to be optimized. Yes, so for example, we say, okay, 3% of the whole domain can be fluid and the rest should be solid. So we want to do is to minimize the energy dissipations between the inlet and outlet boundaries, and everything has to be subjected to the previous constraints mentioned. So the continuous adjoint approach, it works by considering the augmented Lagrangian function, which combines the previous objective function and constraints, and by deriving it in function of its primal states variables, we can find the optimized point of our functions. So at the continuous adjoint equations we have made by handmade derivation, we have found the adjoint system, which differs from the literature publications due to the penalization of the adjoint iconal equation. And also, as we have changed the permeability equation, the sensitivity analysis have changed as well. Also, the optimizers that we have used are powerful optimizers, CDB optimizers and DDB optimizers widely used at the structures optimization. And we have proved in our laboratory that by considering these kinds of DDB optimizers, which works with binary values of 0 or 1 values, we are able to accurately define the solid and fluid boundary definition, which in some cases is difficult with the CDB optimizers. And this work was performed in laminar flow, so the current research takes us beyond to turbulence flow. Everything was written in OpenFOAM in the version 1912. We call it the adjoint topology form solver, and it takes the states equations, the adjoint equations, calculate the sensitivities, uses the optimizers, and check if the convergence criteria is reached to either update the material distribution or give us a final optimized topology. So I will show you quickly two different results at one 2D and other 3D. At first, we make the optimization of a nozzle, which initial CFD modeling shows us that it will have got some vortex at the corners. So we want to avoid these kinds of regions to optimize. So both optimizers are tested. And we see that the DDB optimizer allows us to create a clear, solid, and fluid region, yes, in comparison with the CDB optimizer that shows us the gray regions that we want to avoid in topology optimization of fluids. So both optimizers, they work fine, but the difference is the boundary solid fluid layer definition. And we make the optimizations out to reaching the smooth topologies, yes, each one with its own energy dissipation functions, which are then compared with a common nozzle that you can find in the industry. So when we compare the energy dissipation between the nozzle or the baseline design with the optimized topology, we see that our optimized topology diminishes the energy dissipation by 26% in comparison with the baseline design. After this, we took our results beyond to 3D cases, and where we've got only one inlet and another outlet region, which are diagonal. And when we perform the CFD, we can see that non-intuitive passage can be found due to the large vortex generations that happens inside the domain due to the low viscosities that have been worked on this turbulence regime. Therefore, we optimize the initial domain by considering the CDB and the DDB optimizer. We can see that the CDB optimizer shows us maybe an intuitive solution, which could be the joint of the inlet and the outlet boundaries by means of a diagonal pipe, yes. But the DDB optimizer, due to its binary behavior, it reaches a local minimum difference, and it shows us that this kind of case, yes, which have got some passages that help us to direction the flow and not let the flow go like randomly inside the domain. This can be easily seen by the streamlines we can see that despite this is like a diagonal pipe, we will have some vortex generated at the inlet, yes, and outlet boundaries. And the DDB optimizer, due to the passages that created, it helps us like direction us the flow through the whole domain and not let like this almost random fluid flow. This can be seen at the pressure gradients difference between the inlet and outlet boundaries, where we see that the CDB design has got large pressure gradients. Therefore, the energy dissipation over there is larger. And we can quantify this effect by calculating the energy dissipation. So we can see here the difference between one of the other. So the conclusion of this work is that we have developed this adjoint topology foam solver. There are more 2D and 3D cases that were tested and are now being published. The research is going to be published this year. And we see that the CDB optimizer presents an advantage of stability, computational cost, and the DDB optimizer allows us a clear solid fluid boundary definition, but it is suggested that both optimizers should be tested for different domains. Now we are making optimizations of baselines rotors, and also we are considering near-wall mesh refinement in order to improve the boundary layer definition. Here is my LinkedIn if you want to see more about topology optimization of turbulent flows, and my email if any suggestion or something came up through this work. Thank you.
Thank you very much. I don't know if there are anybody has any questions. If you can type them into the live Q&A sessions part of the conference app, that would be fantastic. In the meantime, I was meaning to ask, I was seeing those images, for example, of the nozzles. Have you tried 3D printing any of these and seeing whether or not your solution matches the physical results?
Yes. Yes, indeed. Well, actually, I'm not working the experimental part. That's another work from one of my colleagues. But there at the Research Center of Gas Innovation, we've got two different 3D printers, one that uses metal and the other that uses plastic printers. And they take these tests and make their experimental results in order to validate the prototypes that are built or optimized.
Okay, it's very interesting.
Yes.
And you are using, what is it, a frozen turbulence approach here?
No, actually, that's one of the goals that was one of the goals of my research in my PhD, was actually develop the continuous adjoint approach for turbulence modeling. So at each optimization step, I solve the turbulence, and not only at the turbulence model, in this case, the spiral mass, but also at the adjoint near wall distance calculation. So the frozen turbulence approach, it has been already like, it was like an intermediate step that was used in the last 4 years in the turbulence modeling of topology optimization. But nowadays in our industry, we don't consider that anymore because several works have already performed turbulence modeling by considering a continuous solving of the turbulence.
Okay, thank you very much. Does anybody else have any questions?
Well, I see plenty of them. Let's try to start solving them in our time. Have we got? So okay, you say what parameter have you used for the optimization? What is the pressure drop in the segments? Okay, I think you're talking about, Andre, you're talking about the objective function. The objective function is the energy dissipation between the inlet and outlet boundaries. And that's the parameter that I have used to make the optimization, and which also includes like the pressure drop between the inlet and outlet boundaries. Another question that says, Leonardo, it says, did I use a steady state or transient for the equilibrium? No, in topology optimization, there has not been performed any transient solution for fluid flow. We use steady states. And okay, another person says, if the solve will be publicity available? Yes, it will. As soon as it been released by the journal, we upload it to the journal platform as well in order to use it. It is an OpenFOAM, of course, an open source. And Sahin told us if I have tried any heat transfer problem where the velocity and temperature field coupled. Yes, I have also worked with compressible flow, made different optimizations on rotors and also pipes. So that's what I've made. Okay. So finally, Revi says, if I make any own solver of modify existing solver, well, for this adjoint topology foam solver, we started by using the adjoint shape optimization foam solver, which is used for shape optimization if we modify it for topology optimization. I think we ran out of time already, Professor.
Yes, I think so. Yeah, so we can move on, but we've got 3 people, so maybe at the end we can come back to any questions. By the way, I'm not getting them through on the website. I think everybody else is, but I can't find the questions, so I'm not going to be able to read them out, so individual presenters will have to do that. Anyway, moving on, as you say, the next talk is by Ophir on the effect of HDR, InfiniBand, and in-network computing on OpenFOAM simulation. So, Ophir Mayor, you'd like to take things away, please.
Hi, do you still hear me? Do you see my screen?
I can hear you. I can see your screen. Looks fantastic.
Okay. So, hi everyone. My name is Ophir Maor. I'm from the HPC Advisory Council. I'm going to present to you the work we have done on HDR InfiniBand networks and introduce to you in network computing. So network computing, what we done on the OpenFOAM on cavity input. If you have any questions, feel free to write them. I could see them, so it's no problem on my side. A little bit on the HPCAI Advisor Council. It's a non-profit organization. Many institutes, universities, research centers are members and try to bridge the gap between HPC and AI. We do a lot of performance benchmarks. We do a lot of competition, student cluster competitions. We do a lot of conferences around HPC and AI. This is part of the members. There's too many, so many icons, but you can see that it's over 10 years, I think, of its existence. Current competition, for example, is the ISC student cluster competition that we run. It's the 10th year. And there is an APAC Asia HPC competition that happened in May. And several conferences upcoming towards September and October in Australia and UK. And you can check more on our website. Under the Advisory Council, we have a resource center, a cluster access, several types of nodes and clusters, Skylake, AMD, Intel, AMD nodes, Rome, Broadwell, different kind of clusters that we allow people to play. If they want cluster resources, they can apply for access under the website. And we have also a community area called HVC Works that we upload several procedures and things, frameworks and benchmarks that we done, and we have the blueprints how to do it, how to redo it. Those are part of the applications that we were testing. OpenFOAM is one of them, and we try to analyze different HPC applications at the time. Let's skip that. I did a little bit about data as a resource. We are moving from, of course, low tech to high tech in the 21st century. If we look at traditional HPC data center, the network itself used to be CPU only. So the CPU was doing half of the communication, the adapter, and the network was just passing traffic, and the compute itself was done only on the CPU side. So the usage of the application was using only half of the time, and the other half was used by the communication to pass between different nodes. When adding RDMA, remote DMA, to the network, the compute element is still using most of the time in compute resources and less time on I/O, because the adapter itself was doing the I/O part, and the latency is very low because the CPU is not handling the send and receive, only the adapter, and the network is very fast. Though the HPC application itself was maybe a bit slower, because some of the collectives, and we'll talk about that, can be done on the network. This is an example with the GPU Direct RDMA. GPU to GPU, instead of going via the CPU memory or the system memory, just going from CPU memory to CPU, from GPU memory to GPU memory, you decrease your time, if you look at the left column, from about 20 microseconds to very few microseconds on different mesh sizes, and that helps a lot. And that's RDMA. So from the GPU memory to GPU memory, just via the PCI switch. No need to go via the system memory to do a copy of the system memory and then to send it. What is in-network computing? So as time going on, we are reaching the limitation of the CPU computation. We want to move and to have the network do some of the computing. So what it means that in some cases, we can offload some of the computation of the application to the network. It sounds weird. It sounds what? It's only a network, but the switches can also do some computation while passing the traffic. And I will show you. This is a MPI all reduce. So you're familiar with that? It's all reduce operation, basic one of the collectives of MPI. If you do it via the network, you reduce significantly the time it's being taken to do the collectives, instead of just CPU is doing the collectives. This is an example how traditionally the aggregation would be done. So let's say node 1 and node 2 or several nodes are replacing information and collecting information on the lower part of the tree. Then another collectives is sending again and replacing information from other chunks on the second level, and then replacing another, sending and retrieving another, collecting another information from the rest of the network. This is one example. But ideally, ideally, what happens here that the network cannot compute anything, it's just passing data. So you have to do those send and receive and computation on the compute nodes. What happens with SHARP? SHARP is a protocol for scalable hierarchical aggregation protocol, that the switches themselves doing the collectives and the reduction on the switches. So you just basically send once to the switches, and the switches return and performs the computation and return the results. When we are talking about collectives such as reduction collectives, such as all reduce, barrier, and all to all, for example, instead of just sending too many packets and waiting for all this latency, you can do that very, very fast with the switches being does the part of the performance, part of the collectives on the switch memory. Moving on, I don't think I need to introduce you OpenFOAM. It's the OpenFOAM Conference, open source CFD applications. So move on. What we did here, we did a test on 2 different clusters. One is an Intel Skylake cluster, and the other one is Intel Ice Lake cluster, 2 different generations of Intel. And we have taken the input, the cavity 3D input, basic input, open source, and we tested that with and without reduction, the sharp. And what we've seen first is that, of course, Ice Lake is the latest Intel CPU that performs almost double the Skylake. And main reason is that Ice Lake is 72 cores per node, and the Ice Lake is 40 cores per node, so more cores, more computation resources. So almost, if you compare the blue and the gray, is like almost double the performance. And it's kind of good scalability, and this is only until 16 nodes that we did. When you compare the performance improvement when we added sharp to the network, a reduction was done with the sharp on the switches, and MPI time, the MPI total time was decreasing by doing that. And the reason is many of the calls is in this profile of the communication are all reduced calls. You see, MPI all reduces the red. So in this case, it was 64 nodes, almost 78% of the MPI calls are all reduced. And going back here, so the all reduced, it means that you take like a sum operation, okay? You take a parameters from each one of them and you perform the sum. Instead of sending it back to the switches, sending it back to another node to perform the sum and send back, you send it to the switch performs the operation itself and send it back, or send it up to perform the sum, the collective sum, like an aggregation tree, and send it up to the root, and the root perform the final sum and send it back. That's why in this case we gain a lot of time, important time for the application time. So again, if we look at the profile, 45% of the time, around 45% is the MPI time. So half of the time is being spent on communication. And if the reduction, the all reduced part is high, and we use the network computation, the network to perform this computation instead of the CPU and the adapters, we gain valuable time on the performance.
Ophir, we should probably keep reasonably to time. 2 more minutes.
Yeah, I'm done. So
sorry.
This is the last session. I want to ask if you have any questions or any comments. Feel free. If not now, you can also feel free to contact me. If you want to play with that or test with that, feel free to contact us via the HVC Advisory Council website. And again, if there are any questions.
I'm still having difficulty reading any, so if you can see any, please do read them out and answer them.
There's a question, I'm not sure how relevant it is. What is the strategy of the change of policy of CentOS 8? So moving towards CentOS 3. I know CentOS is announced that I'm not going to continue with the support We will probably move to another one, to a different one, either Red Hat or Ubuntu. I don't. Sorry about that. I don't have any feedback on that. It's not so much related to what we're doing. Okay, so if no questions, of course, feel free to contact me later. And I guess back to you, Gavin.
Thank you very much, Ophir. That was very interesting. And the final talk from this session is on unsupervised learning of numerical solution in linear elastic solver, and the presenter is Emad Tandis. So the floor is yours, Emad.
Okay, hi everyone. Let me share my screen.
I can see that. It's good.
Okay, very good. Hi everyone. As you can see, the topic of this talk is about unsupervised learning of numerical solution in a linear elastic problem. My name is Emad Tandis. I'm a postdoc researcher at University College Dublin and working with Philip Cardiff and Michael Kalanki on application of machine learning in numerical simulations. Okay, the contents of this talk would be about an introduction of unsupervised learning, then a finite volume informed ML model, which is our approach. And then we introduce a library to use a pre-trained model in TensorFlow and in OpenFOAM, how to use the pre-trained model in OpenFOAM. It can have a general usage for turbulence modeling, for any other application that you know. And finally, I will be talking about how to use our approach and as an initializer in the solid form solvers. The motivation here is we want to build a machine learning model which is capable of generating solution field given an OpenFOAM case. And it does not require prior solution. So it does not require ground truth data. And finally, we want to, as I said, use it as an initializer for the solver, one of the linear elastic solver in solid form. Here, the focus is linear elastic problems, but the idea can be extended to other physics as well. As an introduction to supervised and unsupervised learning from practical point of view, you can see the conventional machine learning model receive X and give you Y. And in the sample of the data set for training of supervised learning, you need pair of X and Y in your data set, which is called ground truth data, which means that for each X, you have to have access to a corresponding Y. But for unsupervised learning, you just need XI. So by giving XI, the model will figure out how to train and how to make a prediction for it. For more detail, let's look at the training process in supervised and unsupervised. The X is input, and ML model actually has a lot of weights or parameters or W or unknown, whatever it is. And having it initialized, it will generate predicted Y, and the predicted Y will given to loss evaluator. Loss evaluator is actually check the quality of the Y, and finally it gives you cost. Cost is average of the square loss for all of the samples. So here finally we have a function. Cost is a function of weights, and training actually means that we want to minimize the cost in terms of weights. But here cost actually includes the definition of loss. So how to define loss? In supervised approach, the loss is defined as square difference of predicted Y and true Y. So you need to have access to the true Y. In unsupervised approach, you don't need to have access to the true Y. So it seems that a loss function in unsupervised is more complex. Here we take the idea from physics-informed neural network approach. In this idea, the loss is defined based on the residual of the governing equation. So if we want the cost and loss to be close to the zero as much as possible. And also in the numerical simulations, we want the residual of the governing equation to be zero. So we use the residual of the governing equation as the definition of loss. But the question is how to reconstruct the governing equation in TensorFlow. In order to do that, we came up with the idea of linear operation. We know that we need to calculate divergence and gradient, and we want to use a finite volume approach. That's why we call the model finite volume informed approach. So in the finite volume, in the Gauss scheme at least, the divergence and gradient are defined in this way. And looking at the formula, we can notice that grad and divergence are function of mesh data, boundary condition, and solution field. The solution field is actually predicted. Why predicted? By the network, but we need to have access to this data. In order to do that, we have created a simple utility in OpenFOAM to generate mesh data, required data from mesh, and boundary condition, and save them on the disk, and a Python script to load them before training starts. In more detail, what the approach looks like. So we have input case here. We have a network which gives us displacement, and we have displacement. We want to use this displacement to reconstruct the residual of the momentum. The way that we are doing that, we are using linear operator, and this linear operator takes the displacement and data structure from the OpenFOAM and deliver divergence and gradient of displacement, and finally it reconstructs the residual of the momentum and gives us the loss. In order to make this method applicable for unstructured mesh, and also in order to make it actually suitable for convolutional network, because convolutional are very good at spatial problems. So we use the concept of dual mesh, in which we have two mesh. One is Cartesian and another is true mesh in the case. So for Cartesian mesh, we define the input on the Cartesian mesh. The inputs are coordinates of the cell and also a mask which defines the geometry, and also fx and fy which defines the boundary condition, and we give them to the some general network, convolutional network, and it gives us the displacement field on the Cartesian mesh. Then we map them into the displacement on the actually true mesh. We use mesh-to-mesh class in the OpenFOAM to do this mapping. And why we do this mapping? Because we want to evaluate displacement on the true mesh and reconstruct the momentum equation on the true mesh. So that's why we do this mapping. And what does the training process look like? Actually, we have a bunch of cases here. All of them are generated from an original case. This original case, we change some part of the boundary or geometry or something that we are interested in, and we generate number of cases, and we give them as the input to the network. So the network start to be trained, and actually training means solution of those of cases, because we don't have any prior solution. So we can say training is also solution of all of the cases together. In order to evaluate this idea, actually we used something like a plate hole. It's not exactly plate hole, but similar to plate hole. For this geometry, we have radius and L, H, and pressure in the circle. Actually, we randomly change them, and we generate 200 samples. You can see them in the right-hand side. They have different radius and different actually length and height and different pressure force. And in this figure, you can see the true mesh and Cartesian mesh. On the top, the true mesh is shown, and on the bottom, you can see the Cartesian mesh. In the left-hand side, you can see the mask. Actually, this mask is 1 where we have geometry, and it's 0 where we don't have. So we simply represent the geometry to the network by this mask. And also in the right-hand side, you can see the boundary condition, and this boundary condition are interpolated from true mesh to Cartesian. So the bottom figures are something that network sees as the input. So we use 500,000 parameters for our network, and it takes about 8 hours for training. Finally, we compare the results with the OpenFOAM solvers, 6% is average of the error for all of the samples in the training data cases, and 10% is maximum of the error. And also we use that network for making solution for unseen cases. So for unseen cases, the maximum of the error is 18% and the average of the error is 8%. And this is what the solution looks like. You can see the top ones are generated by machine learning model. So it makes a prediction, and the bottom one is solution field generated by OpenFOAM. From qualitative point of view, they are quite close to each other. Also, we have used another case. In this case, I call it curved beam. So it is constructed by 2 arcs. Each arc is created by 3 points. We randomly generated these points, and so that's why in the right-hand side you can see we have different geometries, and we want to train our model to learn what is the effect of geometry on the solution field. And as you can see here, again, inputs and Cartesian mesh and true mesh, and how we define the mask and boundary condition on the Cartesian mesh on the bottom. And also the solution field is compared with the OpenFOAM results. And as you can see, the results are close to each other at least. And in the next step, we are trying to use this model as a predictor or as an initializer for the solver in SolidWorks. So in order to do that, we have created a general library which is capable of loading pre-trained model in TensorFlow and make a prediction for us inside the OpenFOAM. So it can have a general application for any application that you have trained your model, you can use it here. This library requires TensorFlow C API to be installed on your system. This is a piece of code that shows how to use it. So for example, here, this is a constructor of the model. So we create a machine learning model with these inputs. There are 3 inputs. One is train model, which is actually, these are some string. The first string is the path of the model. The second and third one are name of the layer as inputs and outputs. And we simply model.predict all of the inputs, which are TensorFlow variable, which are, OpenFOAM variables, and the internal field, which is the predicted displacement field. So that simply we can use it. So I have applied this machine learning model as a predictor in the SolidWorks. In SolidWorks, you have in each solver, you have a function called predict. And in order to use that, we just put this piece of code here, model.predict the internal field. So very clean implementation. And to compare with the result with the base solver, so for the base solver, you can see it could accelerate the solver by initializing data. To be honest, I expected more acceleration, but since I got this result very recently, 2 days ago, I couldn't dig more into the problem. But anyway, it has some acceleration. Finally, in summary, I can say we have used OpenFOAM package to design a finite volume informed machine learning model, and we have generate and organized data using OpenFOAM utilities. And finally, this pre-trained model can be used as a surrogate for the solver, linear elastic solver in the SolidWorks, and also it can be used as an initializer. Okay, and finally, I'd like to express my thanks to Irish Research Council (IRC) for funding body and acknowledge the affiliation of ACORD and IFORM, and that's it.
Well, thank you very much, Imad. Can you see any questions from the audience? I'm sure there are, because it's a very interesting topic.
Sorry, I need to. Look at the. Okay. The first one is say, I would argue that you are doing classical supervised learning. Your features are position vectors of the cell centers and your labels are simply 0, fulfilling the PDE. Would you agree? Yes, actually, supervised and unsupervised, we can look at this problem from different point of view. There are some papers that they call it, when you use a governing equation as something that, as definition of loss. Some people, they call it unsupervised, some other they call it supervised. Yeah, but the idea, I mean, it's about the name, but the idea that you define some finite volume inform approach, the idea is that. But the name, about the name, yeah, I can show you some paper that people call it unsupervised. So there is a challenge for the naming, but yeah, you're right to some extent, yeah. And for the second question, how do you choose the weighting factor for the boundary condition in the loss function, trial and error? What's the effect on the model accuracy and training? How do you choose the weighting factors for the boundary condition in the loss function? Actually, I didn't use any weighting factor. I just finally the loss function is a vector of residual, because, for example, if your mesh has 100 cells, so finally your loss is a vector of 100 cells, 100 values. So I use the loss as a vector, not as a average of them. Another is it possible to develop this type of model for gas liquid multi-phase flow module? Yes, this is finite volume approach. Actually, the main idea behind that, we are using finite volume discretization approach. And you can reconstruct your equation there in the TensorFlow. So actually, it allows you to define any governing equation that you have in your domain. So it's not just limited, as I said, to the linear elastic solver, but we have to check it because it's quite a new idea. It depends on the optimization, and it depends on the training process. It depends on many factors. I mean, I'm talking about the performance, but about the possibility, yes, it's doable. And another one, how do you make sure that BC are fulfilled? Okay, actually, I'm implementing boundary condition. I enforce the boundary condition in the loss function, which means that the loss, when you evaluate the loss is evaluated for each cell, and the boundary conditions are enforced like what we have in OpenFOAM. For example, in OpenFOAM, you don't check the residual for the boundary condition, you just enforce them in the system of equations. Another then from, which approach did you use to make the convolutional network working for different geometries? As I mentioned, I use the concept of dual mesh. So I have one Cartesian mesh. For the Cartesian mesh, it's like an image. We know that convolutional networks are very good at dealing with the image-like inputs. So when you have Cartesian mesh as the input, the convolutional network, we take it as an image or as a tensor and deal with that. And finally, we interpolate the data from Cartesian mesh to actually true mesh. So I hope I answered this question well. I'm not sure. You can ask if there is something vague. So what is the strategy for, sorry, how did you, thank you, it's impressive. Okay, so there are some comments and I cannot see any other question here. So that's it.
Well, thank you very much for an excellent talk and for answering those questions. And I'm sure there will be opportunities tomorrow if anybody has any further questions for any of the speakers. So I'd like to close this session by thanking all three speakers for some very interesting talks, and of course to thank the conference organisers for their efficient and fluid
work on organising the conference. So thank you very much. Have a good evening, and I will see you, I'm sure, tomorrow in one of the sessions. Well, see you virtually anyway.